All right. Volume check. Is this good in the back? A little up? How's this? Too loud? That might be a little too loud. Okay. Sweet. All right, let's get started. I've got almost no math for you today, which I know is a little weird, but who knows? Maybe we'll enjoy that. Today's lecture and sort of the theme of the week as a whole is sort of taking a little bit of a step back. We've done a lot of math, learned a lot about how to learn these models, how to train these models. So let's take a step back and understand how it fits into the bigger picture of what we want to accomplish. I think that there's bound to be a decent amount of overlap with other classes like Data 100 or things like that. So you may have seen some of these things before. Nevertheless, hopefully we can get a kind of a fresh perspective on some of these things, or just really reinforce them into your minds because they're important concepts. So let's see how that goes. Okay. So basically, I think that we know enough now about learning models that we can ask some other important questions. I mean, the first 5 weeks has all been about, learning models, right? We talked a lot about linear models, linear regression models for, linear models for classification. And we talked about how that might actually be even more powerful than it seems because of things like kernelization or just featureization in general, right? So we've talked a lot about how to learn models, but there are some pretty important questions that we really have glossed over up until this point. For example, if I do a really good job at learning my model, so, the parameters that I learn really minimize this loss function that I define, right? Does that mean that I'm done? Does that mean that this is the best model that I could possibly have? Should I, throw my hands up, say this is great, and then just deploy my model and move on, for whatever that means. But is that the case? That's going to be something that we're going to want to examine today. And if that's not necessarily the case, then how do I determine whether I'm satisfied with my model? If it's not just the story of minimize my training loss, then what other pieces might I have that actually really matter? And this is going to come down to this topic that we talked about in lecture 1 about generalization, right? What I'm trying to learn my models for is so that they can make predictions on data that I haven't yet seen, right? And so if that's the goal, I'm going to need a way to sort of try to directly evaluate that, right? And so that's, kind of the general theme of how we're going to try to tackle this question. And lastly, what can I do if I'm not satisfied with this model that I've learned? Maybe even if it minimizes the training loss, it might be not good for, generalization. How do I combat that? How do I, take steps to try to mitigate that? And so answering these questions is going to be very informative, and it's also going to shed light on, this important topic that we have not discussed, which is how to select hyperparameters, right? So we've talked quite a little bit now about different hyperparameters and what kind of effects they might have on the learning and the model that we get out, but we haven't really talked about how to actually choose values for those hyperparameters. We talked about how we can't throw them into the training objective, right? Because a lot of times that doesn't make sense. But we haven't talked about how we choose those. And so we're going to go into quite a bit more detail today about how that's done. Okay. And so what we're going to do is we're going to start with a tiny little bit of math, but this is pretty much the only math that we have for today, in discussing two concepts that people usually call true risk and empirical risk. Okay. These are really simple, so let's not overthink them. Really, all risk is saying is that risk is a measure of your expected loss. Okay, so you have a loss function, right, which measures are these parameters good or are these parameters bad? And this loss function is usually, on a particular data point, xy, that we have, right? We can treat xy as random variables, right, and say that they're drawn from some particular distribution that we care about, right? This is the distribution of data that I'm getting. And then if I treat those as random variables, I can ask, what's the expected loss of some set of parameters theta on this data distribution where I draw xy from that distribution, okay? So this is what people call risk. It's, a fairly standard and straightforward concept. There's nothing that's, particularly complicated about this. Sometimes people also call this true risk, okay? So risk and true risk are the same thing, and the only reason that people call it true risk is to distinguish from a different concept called empirical risk, which we'll talk about on the next bullet. So So then what is empirical risk? Well, empirical risk is basically the average loss that I have on the set of training data that I'm given. So remember, we always start with something like, suppose that I'm given xi, yi from I equals 1 up to n, right? I'm given n data points, right? I can measure my average loss on these n data points, right? And then that's going to give me a measure, what I call r hat, right? My empirical risk, which is a function of some set of parameters theta, okay? It's called empirical risk because there's this other concept called the empirical distribution, which is basically just the distribution over all my training data. So if I have n data points, right, I could say that each one of those data points has probability 1 over n, so all the data points are equally likely. This gives me something called the empirical distribution. And then empirical risk is basically the expected loss on that empirical distribution. Basically, it's just average loss on the training set, whereas the risk, or the true risk, right, is the expected loss over my entire data distribution, right, not just the training data that I've sampled. Supervised learning, at least, you know, in the context of what we studied so far, is oftentimes referred to as empirical risk minimization, because that's kind of what we're doing, right? We're minimizing the loss on our training set, which now we've learned is sometimes called empirical risk. So if you see this term, empirical risk minimization, or ERM, just know that sometimes it's just, you know, oftentimes it's just a fancy way of saying supervised learning, or the way that people usually think about supervised learning, right? It's really just ERM. But really the key question that we want to get into first is, are these two things the same thing? So is empirical risk the same thing as true risk? Is empirical risk minimization the same thing as true risk minimization? Okay, that's the question that we really want to be asking ourselves today. Now, it would be a lot simpler if the answer was yes. If empirical risk and true risk were the same or approximately the same, then, you know, we'd have a lot easier time going through all of this. But unfortunately, that's not going to be the case. And there's going to be a very important distinction between true risk and empirical risk that we're going to have to go into in quite a bit of detail, okay? So you remember in lecture 2 when we were doing math review, I talked about this concept of a Monte Carlo estimate, right? Where if I wanted to estimate the expectation of a particular quantity, the one way I could approximate that is by drawing samples from that distribution and then taking the average and then estimating the quantity in that way, right? So empirical risk, in many ways, looks just like a Monte Carlo estimate of the true risk, right? So if I wanted to estimate the true risk under the data distribution that my training data was drawn from, one way that I could do that is just draw a whole bunch of training data, sample a lot of training data, and then estimate the loss of my model, the average loss of my model, right? And that would basically be an estimate, that would basically be an estimate of my true risk, which is my empirical risk, right? So it looks a whole lot like the empirical risk is just the Monte Carlo estimate of the true risk. So if that were the case, then shouldn't we have that the empirical risk is a pretty good approximate of the true risk, that, you know, these two things are approximately equal? And if that's not the case, then why might this not be the case? Anybody have any ideas? Yes. So the samples aren't representative. That is, at a high level, that is exactly what's going on. Why is it the case that the samples might not be representative why is it that the samples that I'm using to estimate my empirical risk might not be representative of the overall distribution? That's kind of, that's the question that we want to get at, right? They are drawn from the distribution, right? So it seems like that should check out. But for some reason, these samples, in some way of speaking, are not representative of, for example, like the overall distribution of data. Why might that be the case? I'm sorry, one more time? So we do assume that the training data is selected at random, right? So we have this IID assumption, right, on all the xi, yi drawn from the training distribution, right? So it seems like that checks out okay. But what are we doing with the training data? Like, what do we do with the training? Yes? So right, so we're getting at topics involving model misspecification, right, which is a related but more complex topic. Yes. Yeah, exactly, right? So the issue here is that we are already using our training data, right, xi, yi, right? We're using all of that training data to learn theta, right? We are already using that data that I sampled to do something, and that something is to get an estimate of theta that I think is a good fit for that data, right? And if we know anything about things like, statistical testing and hypothesis testing and things like that, like one of the key things that we can't do, right, is we can't reuse a set of data to do two different things, okay? Because then, all our p-values get all messed up and everything, and we just can't trust our conclusions if we don't redraw another set of data in order to do something new, right? So I can use my data to learn theta, that's totally fine, but then I can't use that exact same data to then try to get an estimate of my empirical risk, okay? Especially because my theta was trained, right? It was learned to minimize the empirical risk, right? To minimize the loss on those xi, yi. And so this is no longer going to be a reliable estimate, right, of my true risk because I've already used that data to do something, and that something was to minimize the empirical risk, okay? So doing so, my empirical risk is no longer, on this particular data set, right, is no longer going to be a good estimate of my true risk. So we have very specific terms for these things. So if my empirical risk is low, which means I've done a good job at learning theta, right, but my true risk is high, okay, then we call that overfitting, okay? So the model that I've learned, the theta, has overfit to my training set, okay? It's doing a really good job at explaining all of my training data, but it's not doing anything in terms of, good generalization beyond that, right? Actually doing a good job at predicting on other data points that weren't in my training set. And so this is obviously a big problem, right? If I do a really good job at learning theta, but then that theta is no good at generalizing beyond that, then I haven't really learned a useful model in any sense, right? There is another concept that is sort of a different failure mode where maybe my true risk is high, but also my empirical risk is high to begin with. Okay, what does that mean? It means that I just flat out did not do a good job at learning theta, right? It means that one way or another, the learning process, right, of learning theta actually failed, such that theta is not doing a very good job at fitting the training data, okay? So if that happens, then we certainly don't expect that it's going to do any better on any other data points, right? So it's basically always the case that if my empirical risk is high, then my true risk is also going to be high, okay? Because if my learning procedure fails, my theta isn't even good at fitting my training data, then we don't expect it to do any better on newly sampled data points. Okay, so if both of those risks are high, then we call that underfitting, where my model has basically just underfit everything. It's no good at explaining any of the data, whether in the training data set or outside of that. Okay, so these are by far the two most common failure modes that we can run into. They're very broad, right? There could be many underlying factors behind why we might overfit or underfit. But these are kind of the two key concepts that we want to tackle in order to try to understand how we're going to resolve some of these issues. Okay. So when the empirical risk is low, I've done a good job at fitting my theta to the data that I have, but the true risk is high, so my model is not doing a good job at generalizing, right, to new data, then we're overfitting. When can this happen? Well, this can happen if, for example, the data set is too small. So if I'm only given like a few data points, right, then that might not be enough data to get a proper estimate of theta, right? That could be one particular issue. Another issue is that maybe my model is too, quote unquote, powerful. So I'm not going to very formally define what this means, but we can imagine things like, do I have a model that's a line? Do I have a model that's a complex polynomial? Maybe a linear model with a quadratic or polynomial featurization, right? As my model gets more and more expressive, as it's able to represent more functions, then maybe it's just given too much expressivity to fit all the training data that we have. And this can be especially a problem if it's combined with the first problem of not having enough training data in the first place, right? So if I don't have enough data, or my model is given too much expressivity, right? Then I'm more susceptible to this overfitting problem. And we said if the empirical risk is high, right, which means that we didn't do a good job of fitting the training data in the first place, right, and the true risk is also high because, the model that we learned was just no good, then we're underfitting, right? And this can happen if, for example, the model is too weak. Again, in quotes, because this is not a formal term, but you can imagine things like I have a linear model and like no featureization. So I'm, trying to fit a linear model, maybe the data does not have a linear relationship, right? If that were the case, then I wouldn't expect my model to do very well. And so this could be one key indicator of when we have underfitting. Similarly, we could have issues where, for example, the optimization doesn't work very well. So, for example, if I'm learning a logistic regression model and I'm using gradient descent, but I have a step size that's like way too big or something like that. And then all my loss does is kind of like fluctuate wildly because I'm, jumping between all these different points that none of them actually correspond to the minimum that I'm looking for. That could be another issue that could cause underfitting where, this procedure that I have for learning theta is just not tuned very well, or is just not going to give me a theta that actually represents the true minimum that I'm looking for. Okay, so these both could factor into things, right? If I have optimization that's not working very well, or if my model is just not given enough expressivity, like it's a linear model and the underlying data are not linear. I think a very natural question to ask here is, I'm saying things like the true risk is high, right? The empirical risk is high. What exactly does that mean? Well, the first bullet point, I think, is a little bit more intuitive. So when I'm saying the empirical risk is low, but the true risk is high, really all that means is that like relatively, right? Like if the true risk is higher than the empirical risk, like significantly higher than the empirical risk, right? Then we're getting overfitting. But what does it mean when I say that the empirical risk is high and the true risk is also high, right? There's no more relative, right? That kind of means that they're in the same place. How do I judge whether or not those two things are both high or they're both low? Like how do I even determine that? And so what constitutes high is actually a pretty subjective question and oftentimes just up to the practitioner. Okay, so you're the person that's like, learning this machine learning model. You have to be the one to decide, how well could I expect my model to work for this particular problem? How difficult is this problem? Is there a lot of noise? Are there a lot of outliers? Are there a lot of things that could make it such that the problem is just inherently difficult? If that's the case, then you might set your bar for empirical and true risk a little bit higher than if you thought that the problem was, a little bit easier, right? So as practitioners, we have to be the ones that kind of decide what high even means. And if we have a reasonable belief that our model is not working as well as we think it could, then we might conclude this thing is this thing is underfitting, right? So it's very much, it's at least a little bit subjective. And generally, we're not going to expect that the true risk is ever going to be lower than the empirical risk. Okay, why? Because we're minimizing the empirical risk, right? So what we're doing is we're trying to specifically find parameters theta that minimize the empirical risk, and the minimizing true risk is kind of just like a byproduct of that empirical risk minimization that we're doing, right? So it would be highly, highly unlikely that we would ever have the case where true risk is actually lower than empirical risk when we're doing empirical risk minimization. Okay, so as mentioned, we cannot rely on the empirical risk being an accurate estimate of the true risk. But that's really a problem, right? Because we want to be able to estimate our true risk, right? That's how we said we're going to diagnose overfitting and underfitting, right? Or at least it's very important if we want to diagnose overfitting, right? I can't just look at my empirical risk and say I'm overfitting because that's not the definition. The definition is my empirical risk is lower than my true risk, right? So I need to be able to get an accurate estimate of my true risk if I want to know that I'm overfitting. And remember, we said, what's the problem, right? The problem is that the problem with using the empirical risk to estimate the true risk is that we're trying to use our data set for two purposes, right? The first thing that we're trying to do with our data set is learn theta, right? And what is learning theta? It means minimizing the empirical risk, right? So because we're trying to do that with our data set already, we can't then reuse that same data for estimating our true risk. Okay, this is just like classic data corruption, right? Like we're trying to use one data set for two things that's totally statistically, from a statistical standpoint, that's totally not okay, right? So we need to be somehow making sure that whatever data we have, we're only using it to do one thing, right? Maybe either learning theta, doing empirical risk minimization, or estimating the true risk, which is something that we need to do if we want to diagnose overfitting in particular, right? But actually, from this perspective, emerges really quite a natural solution, right? If I have only one data set, right, but I want to use it to do two things, why don't I just pretend that I have two data sets? So I'm going to take my data set, I'm going to split it into two parts, okay? And then one part I'm going to use to learn theta. That's going to be the part that I do empirical risk minimization on. And then the other part I'm going to use for estimating my true risk. And because that second part I never used to learn theta, it should still be a fairly accurate, as long as it's big enough, it should still be a fairly accurate Monte Carlo estimate of my true risk. And so doing that is going to let me do both of these things that I want to do. First, learn theta, right? That's the ultimate goal. But second, estimate my true risk so that I can diagnose overfitting. Yes? Oh, interesting. That's an interesting question. Let me paraphrase a little bit. So when we talk about overfitting, are we talking about maybe properties that are kind of inherent to our model class, like how expressive it is and things like that, versus properties of perhaps the optimization, being able to find some particular theta star, right? Usually when we talk about overfitting, we're talking about the former. So like how expressive is my model class? Maybe I'm using like featureization that's actually too expressive for the amount of data that I have or something like that, right? And then that's going to lead to problems like, I think we always kind of assume that the optimization, or we hope at least, that the optimization is working really well, so that our optimization can always find that theta star that really minimizes the loss that we've defined, right? And then under that assumption, right, which is not always true, but it certainly makes our lives easier when it is true, under that assumption, we then go and try to tweak everything else in order to try to make sure that we're not overfitting, right? Like if we are overfitting, maybe like collect more data, or like make the model class smaller, or things like that, in order to try to mitigate some of these problems. But we don't ever usually want to make the optimization worse, so to speak. Like we always want to be able to have that be running as smoothly as possible. Okay, so this statistical motivation is actually my favorite motivation into why we need two different splits of our data set, which people usually call training and validation sets, right? This might be a concept that you're quite familiar with at this point. I mean, I think you already saw it in homework in this class, actually, but now we're going to go over it in a little bit more detail. There's a lot of ways to motivate training and validation sets, but I think that the motivation of needing something to learn theta and then needing something else in order to estimate true risk, I think is the clearest way, at least in my mind, to think about it. So we have our data set, right? And what we need to do is actually split this up into two parts so that we can do the two different things that we're looking to do, right? The training set is going to be some split, or some part of our data set, which is usually the larger part, like significantly larger, right? That we actually use to minimize our empirical risk, to learn theta, right? And then the other split of our data set, which we usually call a validation set, right, is something that we hold off. We never actually use that to minimize empirical risk, where we only use that in order to try to get an estimate of the true risk of our current model, our current theta, right? So use the training set for training, i.e. learning theta, and the loss on our training set is already enough to sort of inform us whether or not the empirical risk is high. Remember, this is subjective, right? This is from a practitioner standpoint, trying to understand, is this empirical risk kind of what I would expect for this particular problem based on how hard I think this problem is, right? But if we do think that it's high, then we're underfitting, right? If our empirical risk is high, then we're underfitting. Of course, we also require that the true risk is also high, but like we said before, we never really expect that the true risk is going to be any lower than the empirical risk. So generally speaking, measuring empirical risk is already enough to diagnose and tell us whether or not we're underfitting. Therefore, if we do diagnose that we're underfitting, we need to make sure that we can take steps in order to mitigate that, right? So we also use the training set to make sure that, like, for example, our optimization is working well, right? The thing that we always want to be true, right? Being able to find a theta star properly. We always want to, take steps to ensure that our training loss is decreasing in a satisfactory way, okay? So maybe we need to do things like tune the step size for gradient descent, or do different things along those lines in order to make sure that the optimization is actually going to lead us to a proper optimum. And then we reserve the validation set for diagnosing overfitting, right? How do we do this? Well, the loss on the validation set should be an accurate estimate of the true risk, right? Because we didn't use it for empirical risk minimization. So if I have the loss on my training set, which is my empirical risk, right? And I have the loss on my validation set, which should be a good estimate of the true risk, right? Then I have the two pieces that I need in order to diagnose overfitting, right? I need to see whether or not this validation loss is much higher than the training loss, and if so, I can safely conclude that I am overfitting, and what I need to do is maybe either make my model smaller, collect more data, or do different things along those lines to try to mitigate that overfitting. Yes? That's correct. So we get a loss from the training set and the validation set, and then we compare those to see, are we underfitting, are we overfitting, and then we take steps to try to mitigate those things. And so that leads into a concept which I think is very important, which is the machine learning workflow, which is basically this idea of, like, you're a practitioner, you have a problem, right, a machine learning problem that you want to solve, a data set, right? And now what you want to do is actually, figure out the entire process, the entire workflow that you're going to need to take in order to actually produce a model, right, that does well on this data set, right? How do we actually do that? Well, it's actually not particularly complicated, but let's just walk through it step by step because it's, hopefully we're going to make it crystal clear. First thing that we do, well, let's just, pick some model, right? Like one of these linear models, maybe we pick some kernel that we're going to use or something like that. Some of our hyperparameters, like learning rate optimizers, stuff like that. And then we're going to just learn our model on the training set. Okay, that's going to be step one. So just learn a model on the training set and then just see how it does, right? If we do that and the training loss is not low enough, again, subjective, right? But we decide that, this empirical risk that we're getting from this model is a little bit high and we think that we can do better, then what does that mean? Am I overfitting or underfitting? I'm underfitting, right? If I'm underfitting, that essentially means that, maybe my model wasn't good enough or maybe my optimizer wasn't very good. So I need to do things like increase model capacity. We'll talk a little bit more about what that means, but we've already seen an example, right, where we have like something like featureization, right? If I go from no features to, or like if I go from the original features to like quadratic features, for example, I'm increasing the model capacity, right? Because all of a sudden my linear model is able to represent quadratic relationships, right? So I could do something like that if I think that I'm overfitting, is, improve the richness of the features. Or I could do things like try to improve my optimizer if I think that, this, step size is too big or something like that, right? And then try to do those things in order to fix this to fix this underfitting, right? And then after I do that, I go back to step one and I learn the model again with, this improved, hyperparameters or with this improved featureization or whatever else it might be. Okay, if I do that, right, if I learn my new model on the training set and I'm no longer overfitting, so I'm happy with the training loss, right? If I'm happy with the training loss, then what should I do? I should then measure my loss on the validation set, right? I should see, well, this is doing pretty well from the empirical risk perspective. How is it doing from the true risk perspective, right? Now let's get an estimate of my true risk and see what it's doing. if my training loss is much smaller than my validation loss, right? So if my empirical risk is much lower than my true risk, or an estimate of my true risk at least, then what's going on here? Am I underfitting? Am I overfitting? We're overfitting here, right? The true risk is much higher than the empirical risk. That means I'm overfitting. And what do I need to do? Well, if I can collect more data, that's like basically always the answer, okay? If you can collect more data and that's good data, always do that, okay? That's like you couldn't ask for anything better, but like oftentimes it's not always going to be the case. Like maybe you're just given some fixed data set. You don't have the mechanism to go and collect more data on your own, right? But if you can, always start there. If I can collect more data, great. Otherwise, I might need to do other things like maybe decrease my model capacity, right? Maybe I'm using featureizations that are like too high. Maybe I need to like reduce the order of the polynomial or something like that, right? But in general, we're going to do something in order to try to mitigate this issue, right? That my true risk is much higher than my expected risk. And then we're going to go back to step one again and try to learn a new model on this training set with these adjusted hyperparameters, okay? So I basically just, do this over and over and over again, right? Maybe first I'm underfitting, so I, increase my model capacity, and then after I do that, I'm overfitting. So now I gotta, do things like collect more data, and then I go back and I'm underfitting again, and then I just, gotta, perform this loop however many times it takes in order to not be overfitting or underfitting, right? We want to be avoiding both of these things. And if finally we get to the step where we're not overfitting or underfitting, then we're done, okay? Then we're finally good, and this is a model that we can be happy with, okay? So the original question that we had on the first slide, if my model minimizes the training loss, are we done? The answer is no. Okay, you're only done after you've gone through this entire workflow, and you can be confident that your model is not only good on a training set, but it's also going to be able to generalize outside of your training set, okay? So that's the answer to that first part. Yes? If you're unable to collect more data, can you just resample from your original data? So I think that the process that we're describing here about like learning theta on a training set is already assuming that you're doing that with all of the data, right? So there's not going to be any resampling that can really be done because we're already using all of it. Yeah. Right. So that is one way that we could resample our data, but that's kind of for actually, am I going to talk about that in a couple weeks? Yeah, that's kind of for like a different purpose of like trying to at least in the context of machine learning, right? Like there's other fields that like, use it for different purposes, but for machine learning, what we're trying to do is we're trying to train multiple models all on the same data set, right? But we don't want all those models to just agree on everything, right? We want them to be sort of like, accurate probabilistic estimates of what the model should be on the whole distribution of data. And then so that's where statistical bootstrapping kind of comes in order to do that. But I don't necessarily know if it has a whole lot to do in terms of like fitting into this overall workflow. Yeah, I think I saw this first and then over there, yeah. Oh, does the validation set always have to be the same, or can we sort of like re-split our data? Yeah, so a lot of the times, at least these days, people usually just fix out a chunk of data to be validation and then just sort of keep it that way forever. This is for various reasons like efficiency and all that other kind of like, practical stuff. We will talk at the end of this lecture about cross-validation, which doesn't do that, right? It essentially treats different parts of your data as the validation set. Actually, every single time you do this training validation process, right? So we will talk a little bit more about methods that don't necessarily have to do that. Over here and then back here. Okay, yeah, we'll talk about that at the end of lecture. Yeah. Good question. Yeah, so when I say collect more data, I am talking about adding that to the training set because what we want to do is make it not so easy to minimize the training loss, right? If we're overfitting, that's the goal, right? But it doesn't hurt to add more data to the validation set as well, right? Like that's not necessarily going to make the model training better, but it will give us a better estimate of the true risk, right? The more data we have in our validation set, the more accurately we can estimate true risk. But if we think that we're already estimating true risk pretty well, then maybe there's no reason that we need to make the validation set bigger. What does you're done mean? Okay, I think that this is actually a pretty good question that, that everybody should think about a little bit. So, if you're in industry, you graduate and you go get a job after this, and, you're a, expert, machine learning practitioner, maybe what it means is that you deploy your model, right? Like you've trained your model on some data set and now you're ready to deploy it into the real world and have it, do real things like commercial applications and things like that, right? In research and, in things like competitions as well as in this class, right, you're already, doing something with Kaggle, right? What it means is that you report your model's performance on some test set, okay? So that's, another separate set of data that's completely disjoint from your training set and your validation set, right? The test set is reserved for reporting final performance only, and it should never, ever be used for anything else, okay? Why is this the case? Well, the test set is kind of the gold standard estimate of your model's generalization capabilities, right? It's the gold standard estimate of, I finally have a model that I've output, some theta, right, that I've deployed, and I want to know how well is it going to do on new data that it hasn't seen before, right? The way that I do that is by measuring performance on a randomly sampled set of data that had nothing to do whatsoever with any part of the training process, right? And that includes the entire workflow, which includes training and validation, right? So because we are using the validation data to choose some things, right, it can be the case that that validation loss becomes an overestimate of how well our model is actually going to do, right? Usually not by much, right, because we're using it only to pick maybe a few things. Certainly not as bad as the training loss, right, which is just empirical risk. We're just flat out minimizing, right, using very good algorithms, right? But it still can be the case that the validation loss is going to overestimate how well our model is going to do, right? So what we really need is something that is, in some sense, like it's never been touched, right? Some set of data that we've never even seen before, and that's what we're going to use in order to report performance. Doing so is going to give us kind of the best estimate of how well our model actually generalizes. And for that reason, we should never use the test set for anything other than just reporting final performance. Okay, now let's talk a little bit about selecting hyperparameters. We've actually already touched on this in the workflow, but it wasn't made extremely explicit, so I just wanted a slide that makes it a little bit more explicit. So what are some examples of hyperparameters that we've seen so far? Lambda, what is lambda? Yeah, great. That's actually the first one I listed too. So we have L1/L2 regularization strength lambda, for example, like in ridge regression or lasso, right? That's a good example. What else have we seen? Yes. Fantastic. That's the second one. So the soft margin SVM slack penalty C is also a hyperparameter, right? Something that we pick ourselves, right? Lambda we pick ourselves, C we pick ourselves, and we remember, if this doesn't come back to you right away, it's a good thing to review. Just remember why we can't bundle those things into our parameters that we minimize with the training loss, right? It's a very good thing to understand why lambda and C can't be optimized using the training loss alone. Okay, these are hyperparameters that we have to pick ourselves. Anyone think of any others? Yeah. Xi, our slack variables, right, are actually training parameters, right, because we're minimizing that alongside everything else. Yeah, that's a tricky one, though. Yes. Yeah, absolutely. So things like learning rate, alpha, right, and also even things that you might not think of because they're not scalars, right? So lambda, C, alpha, they're all scalars, a little bit easier to reason about. But we can bundle other things in with this general concept of hyperparameters, right? Like, for example, what features do we choose? Do we use quadratic, some higher order polynomial, RBF, no features? All of this also can be bundled in with the general concept of hyperparameters, because really a hyperparameter is just something that we have to select ourselves. That's basically, at least practically speaking, where we draw the line between hyperparameters and parameters, okay? Parameters are optimized automatically by whatever algorithm that we're using. Hyperparameters we have to select ourselves. Okay, that's really the only key distinction that matters. And we're selecting those hyperparameters not based on just minimizing the training loss, remember, right? Because that leads to values of like lambda and c that are just no good, right? We are selecting those hyperparameters in such a way that we think that they're going to lead to a good model, right? And we sort of always left it at that level of vagueness, right? We never really talked about exactly what a good model means. This lecture, we've defined that a little bit more concretely, right? Where a good model is something that generalizes well to data outside of my training data set and is going to give me good generalization performance by not overfitting or underfitting, right? And so we select these hyperparameters in order to ensure that we're neither underfitting nor overfitting. That's the high-level goal that we have when we're trying to pick these hyperparameters, right? And so this selection process is actually a part of the earlier workflow that we had. Okay, so let me give you a little bit more of a concrete example. So let's say that we wanted to select a value for lambda. Let's say that we were doing like ridge regression and we wanted to do L2 regularization with lambda, and then we pick a value of lambda, right? And then we figure out that our training loss is too high. Okay, well actually wait, let me think about that for a second. I'm trying to do this on the spot. So we have L2 regularization, right? And then we pick a value of lambda, and we figure out that our training loss is too high, okay? So what does that mean? That means that we're underfitting, okay? In what direction should my lambda go? Should I increase my lambda, like increase my regularization strength, or should I decrease my lambda? So I see some this, okay? So I want to decrease my lambda, my regularization strength. Why? Because as I decrease my lambda, what I'm focusing more on is trying to fit my training data, right? From a high-level perspective, right? So if I'm underfitting, it means that I'm not yet fitting my training data well enough, right? So I want to do things in order to try to make sure that my training data is fit better. And decreasing my regularization is one way that I could potentially try to make that fit a little bit better, okay? Consequently, if I'm fitting my training data too well, right, and my generalization performance is no good, right, and that means I'm overfitting, what do I want to do? I want to bump up that lambda, right? I want to make it bigger such that, maybe I'm no longer fitting the training data quite as well, but I'm going to be able to generalize a little bit better to data that I haven't seen previously. So this is the kind of the high-level idea behind how these hyperparameters fit into the workflow that we already discussed, okay? We want to pick values of these hyperparameters such that we can fix both underfitting and overfitting, right? And doing so is going to require, fairly careful selection of these hyperparameters. It's not an easy process, but at a high level, that's, the goal and how we're operating in order to try to get to that goal. Okay, so now let's talk a little bit about cross-validation then, since people were asking about it. I think it's quite interesting, actually, that, back when I was learning about machine learning, like cross-validation was such an important concept. Like, you'd learn it in like lecture 1, and then, people would just harp on it all the time. And, now in today's day and age of machine learning, I don't think that cross-validation is actually all that important anymore. With people doing a lot of like deep learning these like deep neural networks that are like really expensive to train and all that kind of stuff, the training validation process is usually much more limited, okay, because we can't afford to do all of these training validation loops because the models are just so big and they take so long to train, and the data sets are so large that we really just can't afford it anymore. And so these days, especially in deep learning, it's actually very common to not do cross-validation and only have like a single training validation split that we use for all of training. So basically what we've already described, right? Nevertheless, cross-validation is still an important concept and we should learn it. It's just good to know that it's not exactly the gold standard that it once was. So what's the issue with validation and what does cross-validation try to do? Well, basically, it's kind of like what we already said. So setting aside a fixed portion of our training data to do validation can become an issue, actually, if we repeat this training validation workflow many times. So if I evaluate my validation loss and I say like, oh, I'm overfitting, let me tune some things, and then I evaluate it again, and I was like, oh, I'm overfitting again, let me tune some things, and you just do this over and over and over again. Essentially what we're doing is now the validation set is part of the model selection procedure, right? We are using information from our validation set in order to try and find the best setting of our hyperparameters, find the best model that we can, right? So it's not quite as direct as learning on the training set, but it does have an influence on the model that we pick, right? What this means is that we might actually, in some sense, start overfitting to the validation set, okay? Where our validation set actually starts to become, did I say overestimate? I should say underestimate, right? Our validation set should become an underestimate of the actual loss that we're going to incur, right? So basically, if I use the validation set too many times, right, then it no longer becomes this like pure data set that I'm only using to estimate the true risk, right? Like if I only used it once, then that would be a good estimate of the true risk, but I am using it in this loop in order to try and find the best hyperparameters and things like that. And so because I'm doing that, it might be the case that we could start overfitting to the validation set, which is, by the way, the reason that you should never use the test set for anything besides reporting final performance, right? Because this same thing could happen with the test set if we weren't as strict about that. So actually, an alternative approach, which better utilizes the data set, right? So it doesn't have this single split that we were talking about, right? But is more computationally expensive, right? Is what's known as cross-validation. And the high-level idea is actually pretty simple. Once we get into the details, things start to look a little messy. But the high-level idea is really simple. It's basically if I'm doing this evaluation, right? So I've picked my model, I've picked my hyperparameters, I have learned my theta, right? Now I want to know, is this model overfitting? Well, what I need to do is I need to compare its training loss to its validation loss, right? When I'm doing that, what I can do is instead of having a single validation set, what I'm going to do is I'm going to split out, right, different pieces of my training set into validation, and then train on whatever I didn't split out, and then evaluate on the validation set. And then do that multiple times for different splits of my data, and then average all those results together in order to get an estimate of how good that model actually is, okay? So then we average the results in order to estimate how good that particular setup is, that particular model choice, all the particular hyperparameter choices, things like that, okay? This is really the high-level idea behind cross-validation. There are some details that we can get into that get a little bit more complicated. Perhaps I think that this diagram is kind of the clearest thing that I could find in terms of actually illustrating what cross-validation actually looks like. So let's actually go through this in a little bit of detail in the 2 minutes that we have left. Okay, this all data. Ignore this. Okay, we don't actually want to talk about this. What we're talking about is the training data, right? So all data actually includes both the training set and the test set, but remember, we're not touching the test set for anything, okay? This test set is reserved for the very end when we're doing final evaluation, okay? So ignore this part for now. All we're focusing on is this training data set over here. So one example of how we can do cross-validation is what's known as k-fold cross-validation, okay? Where k is going to be basically how many different splits am I going to have in my training data. So this is an example of 5-fold cross-validation, where basically I take my training data, and instead of splitting my training data into a fixed training set and a fixed validation set, I'm going to split my training data into 5 different pieces, fold 1 through fold 5. Why are they called folds? I don't actually really know, but it doesn't really matter, okay? So I split my training data into 5 different pieces, and now what I want to do is I want to evaluate a single setup. Okay, I'm going to evaluate one setting of my model plus my hyperparameters, okay, in order to understand, is that a good setting of my hyperparameters plus my model, or am I going to be overfitting if I do that, right? How do I do that? I'm going to repeat training 5 times, okay, where each time there's a different fold that's my validation set, okay? So all these blue ones, that's what I'm not training on, and then all the rest of the data is what I'm going to train on, okay? So I train on folds 2 through 5, and then I evaluate on fold 1, my validation set. I repeat the same thing for fold 1 plus 3, 4, 5 is my training set, and then 2 is my validation set, so on and so forth, right? And then on each one of those validation sets, I measure what's my validation loss, and I compare that to my training loss, okay? And in doing so allows me to understand, am I overfitting or am I underfitting? while using all of the data that I have and never actually having to hold out a fixed set of validation data that I never get to see, right? So this is a more efficient use of my training data than if I were to do a fixed validation set. And then at the end, in order to estimate my overall validation performance, I just I average all of the validation losses together into a single number, okay? And that's how I evaluate a single setup, like a single setting of my model and my hyperparameters. Okay, that's all the time we have for today, but I think actually what's really important is the view on your own. Go back to the first slide that we have, look at those questions that we put on the first slide, and then make sure that you know how those questions actually get answered now. So that was the key point of this lecture. Okay, so we'll do that, we'll assign that as soft homework that you can do on your own. Okay, thanks.